My name is Antony Polukhin. I'm one of the Boost C++ libraries developer, and I work for Yandex. This is my first time at CppCon. I'm a little bit nervous. So in attempt to amuse you, I've came here with the most complicated talk I have. It's about reflections in C++ 14, how to implement them without macros, markup, nor external tooling, mostly metaprogramming tricks. So here comes the introduction. Let's create some structure. It will be a plain old data structure, and let's name it a complicated structure. We've got a complicated talk, we will need a complicated structure. With that complicated structure, we can write the following code. We've got a main function, there we create an instance of our complicated structure, aggregate, initialize it, and after that, we attempt to put that instance into the std.cout. And at that point, a compile time error must occur, because we haven't defined nor declared the ostream operator for our complicated structure. However, the code will compile. And what's more interesting, the code will correctly output the content of the variable. We can go back, change names of the fields, change the name of the structure, change values. The code will continue to compile, and it will correctly output the content of the variable. So, how does it work? Let's take a look at the header with an ugly name magicget. In there we will find an ostream operator. That ostream operator is pretty simple. It calls a flat-write function. Inside the flat-write function, there is some logic that outputs curly brackets and a long and ugly code line in the middle of the body. In the middle of that code line, you can see a flat tuple size meta function call. The interesting thing here is that we've got a stud tuple size in the standard library, and that stud tuple size works with tuples. But here T is a user-provided structure. That's interesting. Let's move on. Print function. It has some logic to output or not output commas. And after that, there is a flat-get function call, and the comment that flat-get works exactly like stud-get. But again, value here is a user-provided structure, not a tuple. So the ostream operator detects fields count in your user-provided structure, and then iterates over the fields of your structure, outputting field one by one using the index of that field in your user-provided structure. Wow! How is that possible? And that's the theme of today's talk. We'll try to implement those functions. We'll try to implement function flat-get that returns field from your structure by index. And we'll implement flat tuple size function that returns elements count in your structure. Let's start with something simple. Let's start with fields counting for your structure. Here's the basic idea. We've got some plain old data structure T. With that structure, we can write the following code. We can write T curly brackets from some arguments. It's the aggregate initialization of your structure T. That code will successfully compile if arguments count is less than or equal to the fields count in the structure, and the if type of each argument matches the corresponding type of the field in the structure T. From that, now we'll try to extract the fields count. Here's how. We try to aggregate initialize structure T with a huge, insanely long amount of arguments, and that will fail to compile. We drop off one of the arguments, it still fails to compile. We repeat the procedure. At some point, when the arguments count will be equal to the fields count in the structure T, bam, the code compiles. A few things to take care of. First of all, how many arguments do we need to start with? My thoughts are the following. If our structure T contains only char, unsigned char, or signed char, the data types, then the size of that structure will be equal to the fields count in the structure. If our structure T contains other data types, like integers, pointers, then the size of the structure will be greater than the fields count in the structure. Now, That means the following. We can start initializing our structure T with arguments count equal to the size of the structure T. If that succeeded, great. We've got fields count equal to the size of the structure T. If that failed, we drop off one of the arguments and try again. If that succeeded, super. We've got fields count in the structure T equal to the size of the structure T minus 1 because we dropped off one of the arguments. If that doesn't succeed, we drop off one of the arguments and we get a problem. The problem is following. We do not know the type of the field at all. Even if we correctly guessed the arguments count, that won't help us. That line, that argument initialization of structure T, will fail to compile. We've guessed the arguments count, but we do not know the type of the field. That's a problem. Let's work around it. Here's the workaround. It's pretty simple. We'll create a structure. I've named it Ubik because it seems to be a nice name and I like science fiction. That Ubik structure has an implicit conversion operator to any type. What does it mean? It means that instance of Ubik could be implicitly converted to any type. Integer, float, double, string, vector, user-provided structures to anything. That's the solution. Now, instead of knowing the exact type of the field, we can use that structure Ubik. So, here's the whole recipe. We try to aggregate initialize structure T with arguments count equal to the size of the structure T, where each argument is an instance of structure Ubik. If we've guessed the arguments correctly, the arguments count correctly, then during the aggregate initialization, all the instances of Ubik will be implicitly converted to the type of the field. The implicit conversion operator will be called. That's it. The expression compiled, we count the Ubiks, we count the Ubiks, and it will be equal to the fields count. If that failed to compile, we drop off one of the arguments and try again. That's the idea. Now let's implement it. For that, we slightly modify our structure Ubik. Now it has a template parameter, so now we can use that Ubik structure in template arguments expansion pack. Also, we will need to use a std index sequence. Yesterday, Stefan was talking about that stuff. Make index sequence that evaluates into the std index sequence with some index sequence. Now, are you ready to see the code? Okay, it's not so scary. Only 2 lines. Here's how they work. We've got 2 functions. Both of them have the name detectFieldsCount, but the first function is slightly more specialized. So when the compiler sees detectFieldsCount, triangle brackets, T, the compiler will try to use the first function. The first function has a trailing return type, and inside that trailing return type, there is our aggregate initialization of structure T. We've got a decltype, T, and aggregate initialization. Now, if we guessed the arguments count correctly, the compiler will use that function, and in the body of that function, we write the arguments count into the output variable out. If we've failed, and we've provided wrong arguments count, the compiler will think, hey, that's a substitution failure. Not a problem, not an error. I'll just use a function with the same name that is slightly less specialized. And the compiler will use the second function. Second function drops off one of the indexes, in other words, drops off one of the arguments, and calls detectFieldsCount again. So it will call either the first function or the second. So in linear time, we'll detect the fields count in our user-provided structure T. Now, the best part of this technique is that it works even with non-plain old data types. It works with any type that is aggregate initializable. You can write a structure with string, vector, integer, and that technique will work well. We can apply this technique even if your structure has bit fields. Just multiply the initial arguments count by 8 and you're done. We can count even bit fields. Was that hard? Yes? No, this is going to be hard. How to get the type of the field? We already have our aggregate initialization of structure T. During that aggregate initialization, an implicit conversion operator of structure ubic is called. And inside that implicit conversion operator, we do know the type of the field. It's the exact type of the field of the structure T. That's it. Now we need to grab it and pull to the outer scope, where we can do something with it. And there are some problems. For example, there is no way to assign a type to some variable and then get the type back from the variable. Yes, there is Boost.TypeIndex and Boost.TypeInfo, but they're useless at compile time. You just cannot extract the type back from them. That's a problem. Workaround. For a workaround, we will need to remember what is a plain old data type, roughly. The committee likes to change the definition every 3 years. So, plain old data type is a class or structure, and all the fields of that structure are either public or private or protected, have the same access modifier. We're interested only in public plain old data structures because they are only aggregate initializable. But that's details. The interesting part here is that all the fields in the plain old data type must be other plain old data types or fundamental types like integers, pointers, and nums. Now let's forget about the nums and pointers for a few moments, and we'll be left with integers and some stuff like stud null pointer type. Now, the remaining fundamental type, that's not much of them. There's less than 32 fundamental type remains. And here's the idea. We assign a unique identifier to each fundamental type. For example, unsigned char has an identifier 1. Short has an identifier 7. Now, that identifier is an integer. You can use a stud size t for that. And that integer we can put into some output variable or output array, pull it to the outer scope from the implicit conversion operator, and there you can convert identifier back to type. We've extracted the knowledge of the type from the implicit conversion operator. That's great. Let's implement it. This is only the beginning. Get ready. We modify structure ubic. This time it has a pointer to some output array. Unfortunately, it's called here ref because I'm bad at naming. So, we've got an output variable ref. It points to some output array. We modify the implicit conversion operator. Now it has a type to ID function call that converts type to ID. That was surprisingly. Now, we provide the type to that function and get an identifier of the type. That identifier we write to the output array, and here it goes. We've done. Now, we need to generate a lot of type to ID functions. We need to register all the fundamental types. For that, we'll use a macro. Yeah, I know that the topic of the talk is without macro. But I was talking about macro that are used by user. We can avoid this macro. This macro is only for our own simplicity. We can just write all those functions by hand. That would be boring. So I've used macro. I've used it, and after I undefine it, user doesn't know about the macro. Now, what does the macro do? It writes down two functions. First function is type to ID, that converts type to identifier. And second function is ID to type, that you already guessed what it does. It converts identifier back to type. Here, identity is an empty structure, just used for metaprogramming. Size underscore t underscore is a stud integral constant from stud size underscore t. It's an alias. You can see the same namings in Boost metaprogramming library. It has, for example, int underscore. That is an integral constant from int. Here we get an integral constant from size t. Now, let's register all the fundamental types. Not all of them are on the slide. Some of them are on the slide. Here you can see that unsigned char has an identifier, for example, 1. Short has an identifier 7. And we haven't used the identifier 0. I'll tell about the 0 a little bit later. Now, let's write a function. That function will extract the knowledge about the fields from our structure T, and will put that information about the fields into the output array types. All the interesting things are located in the body of that function. There is an aggregate initialization of structure T. Here we create a lot of ubic variables, and during the construction we provide an output array types to those instances of ubic structures. After the aggregate initialization, output array types contain the information about all the fields in the structure T. Please note that the function is constexpr. We can do all the stuff at compilation time, no runtime overhead. Now, let's convert those identifiers back to type. At line 1, we receive a stud array of identifiers. Well, not stud array. Stud array is not constexpr till C++ 17. So it's a handwritten stud array that has a constexpr operator square brackets. Now, at line 1, we get an element from that array, convert it into the integral constant. At line 2, we convert an integral constant back to type. And at line 3, we create a tuple from those types. So, we get a tuple. First element of that tuple is the type, and that's the exact type of the field in the structure T, of the first field in the structure T. In other words, we've got a tuple that has exactly the same layout that the user-provided structure. I'm simplifying here a little bit. Now we can do something disgusting. We can take a pointer to user-provided structure and reinterpret cast it to the stud tuple that we've just done. After that, we can work with pointer to stud tuple, that is actually a user-provided structure, and we can access fields of the user-provided structure by index. Why I've said that it's not exactly stud tuple? There's no guaranteed order of elements in stud tuple. Some implementations of the standard library create elements starting from the beginning of the tuple and store them in the order they appear. Some libraries do that in the reverse order. So the actual implementation has its own implementation of stud tuple, has its own tuple. Now, that's it. We extracted the knowledge of the fields from the structure T, and everything at compile time. A few more things to solve. Pointers. There's a lot of pointers. There could be a pointer to integer in user-provided structure, or pointer to integer, or const pointer to volatile pointer to const pointer to volatile pointer to unsigned char. You can continue. The problem here is that it's an insane amount of combinations. We just cannot register all the combinations in our list of fundamental types. It will take megabytes of code and insane amount of work. Let's work around it. We get a type to ID function, and it returns stud size t. Size of stud size t is 64 or 32 bits, depending on your platform, sometimes even less. Now, we've got less than 32 fundamental types, and that means that we're using only 5 bits from stud size t. And that means that we could reuse the remaining bits to encode information about the pointers. We've got not so many combinations, like pointer, const pointer, volatile pointer, all of them fit into 3 bits. Now, at this point, nobody understands what I'm talking about. That's why here's an example. If a structure T contains a field unsigned char, then that field will be encoded as you can see on the right part of the slide, in binary form, the less significant bit contains the identifier that this is an unsigned char. Unsigned char has an identifier 1, less significant bits contain information that this is unsigned char. We've got 1 here. If we add a pointer to our unsigned char, the most significant bits will change. Now they contain information that this is a pointer, and the less significant bits contain information that to char, to unsigned char. If we change the pointer type, the most significant bits will change. Now they are telling us that this is a const pointer, and the less significant bits that it's a pointer to unsigned char, that it's just an unsigned char. If we add another level of indirection, other most significant bits will change. Now the most significant bits contain information that this is a const pointer to pointer, and the less significant bits telling us that it's unsigned char. If we change unsigned char to short, most significant bits will remain the same. Less significant bits now contain 7. It's the identifier of the short. Now, how to implement it? It's pretty simple. All we need to do is to add 4 type-to-ID functions that work with different pointer types. Inside, they add the knowledge about the pointer to the identifier. We will also need 4 ID2Type functions that will be called depending on the identifier we're working with. If the identifier has the bits that this is a const pointer, the first function will be called. If identifier has the knowledge that this is a pointer, the second function will be called. Here, if extension is an alias for std enable if and some nasty expression that detects what pointer we are working with. What pointer is encoded in the identifier. Enums. Now the question, how to encode enums? And the answer is, I don't know. I don't know a good solution. User at any point can create its own enum. It could include our header and then create a lot of enums. They're all fundamental types. But we cannot register them in our list of fundamental types. They're not created yet. So here's a workaround. Instead of really encoding the enum, we'll just encode the underlying type. Here's a type-to-ID function that works with enums, and inside it just calls std underlying type and forgets about the enum and just encodes the underlying type of the enum. That's it. Now, what to do with structures and classes that appear as a field in our structure T? And the answer is, well, nothing good. The problem is exactly the same as with enums. We cannot register all the user-created structures in our list of fundamental types. It's just impossible. But we can do the same thing as with enum. We can encode the fields that this structure contains. It will be some kind of flattening. For example, if our structure T contains another structure foo as a field, and structure foo has an integer, then we'll be encoding our structure T as if it just has a field integer. We'll totally forget about the foo structure. If foo structure contains integer and short, and foo structure is located in our structure T, then we'll be encoding T as if it contains integer and short, and that's all. We totally forgetting about, English is not my native language, we're totally forgetting about the structure foo. Now, how we'll do it? We just call the function array of type IDs for the field. You already saw that function, it returns an array of type identifiers of the fields. And yes, it returns an array. All the previous type-to-ID calls were returning to size T. Here, type-to-ID returns an array. We need to fix our UBIC structure again. This time, we change the implicit conversion operator so that implicit conversion operator can work with arrays. Here type IDs could be an array. After that, we call a member function assign. There are two member functions assign. First member function works with stud size t and just outputs that identifier into the output variable. Second function assign works with arrays, and it copies all the data from array to the output array. We could probably use std_copy here, but this would be available only after C++17, if we'll be happy, if that happens. We're working in C++14, so we need to do it by hand. And here comes the problem. When we're copying arrays, we must take off indexes. Data that we are writing must not overlap with previous fields or with fields that go after that. So let's take care of indexes. From first slides, we already know that size of the structure t greater than or equal to the fields count in that structure. That means that if we're encoding structure t, we need up to the size of that structure elements in the output array. If our structure t contains a field that is a user-provided structure, for encoding that field, we need up to the size of that field space in the output array. And after a few minutes of thinking, I don't give you those, after a few minutes of thinking, we will know that the index where is it safe to write equals size of previous fields. And I think that you're totally lost at this moment. That's why I've added an example. Structure foo1. It contains a short and unsigned char. Size of the structure foo1 is 4. Well, size of from that structure will return 4. So we need an output array that has 4 elements. You can see that output array on the right part of the slide. First field in structure foo1 is short. It has an identifier 7, identifier of the type short. And that's the first field. No fields before that field. Size of previous fields equals 0. We need to write 7 at index 0. Second field is unsigned char. It has an identifier 1, but size of previous fields equals 2. We write 1 by index 2. Let's make it harder. Structure foo2. Size of structure foo2 equals 6. First field is unsigned char. It has identifier 1. It's the first field. Size of previous fields equals 0. So we write 1 by index 0. Then goes the foo1 structure. And we'll just encoding it as if all the fields of the foo1 structure are located in structure foo2. That means when we start encoding short, short has identifier 7, identifier of the type short is 7, but the size of previous fields equals 1 with get and unsigned char before the short. So we write 7 by index 1. Now, final field in the structure foo1, it's unsigned char. It's not the first field. There are 2 fields before that. We get a field short and field unsigned char. Size of those fields equals 3. We need to write information about the last unsigned char by index 3, and unsigned char has identifier 1, so we will write a 1 by index 3. That's pretty it. Now, here you can see there are some zeros. Zeros are unused elements, just spaces, gaps. We need to remove them, resize the array, and then we can work with that small array. That's pretty it. You can do that with standard algorithms after C++17 if everything goes well. But we're in C++14, we need to implement that by our own hands. Now, a few more examples. That's the place where I scheduled drinking water. Yes, I'm a control freak. I scheduled place to drink water. Now, the implementation. function type to array of type IDs. In the body of that function, first line, we receive the offsets. It's just offsets. Those offsets are used during the instances of ubiq construction. In the second line, we do the aggregate initialization of structure T. We create a lot of ubiq instances, and each ubiq instances get the offset, whereas it's safe to write the information about type or multiple types. That's it. After that line, we get all the types of the structure, all the information about the fields of the structure in the output array types. The other code didn't change. We just convert identifiers back to types. Now, at this point, you're wondering, probably yes, do we really need all those overcomplicated metaprogramming tricks? They're just insane. There's a reinterpret cast in there. Do we really need it? Where can we use it? Here's the answer. The first place where can you use it, you can write comparison operators only once. And that's all. They will be working with all the user-provided structures. That's great. That's something that Bjarni was proposing, and that was not accepted. Unfortunately, instead of the good solution, now you have a handmade stuff with reinterpret cast in it, but it works. And has some limitations. Now, you can also write heterogeneous comparators. You can write a flat-less function that accepts two different structures and just compares them field by field. You can write generic IOStream operators that work with any user-provided structure. You already saw that at the first slides. You can write a hashing function that will work with any user-provided plain old data type and will work correctly, even if that structure has unused spaces in there, some gaps, some non-normalized doubles, it will work. You can write user-defined serializers. For example, when I've told about that technique at the Boost mailing list, some people were just, yay, that's what we need. Here's the story. We'll get 1,000 structures. We're hardware developers, we'll get 1,000 structures. Those structures represent some low-level protocols. The problem here is that we need 3 serializers for each structure. Because we've got different underlying hardware, different wires, we need to send them in a different way, so we've got 3 serializers for each structure. We've got 3,000 serializers, and that's awful. Using EO technique, we can have only 3 serializers, and that's it. We do not need any more. That's great. They were really happy. All the techniques allow us to open the way to use basic reflections. We can create new type traits, is continuous layout, is padded. We can even write the C++ 17th type trait has unique object representation, but in C++ 14. We can create new functions. For example, punch hole function that detects unused bits in user-provided structure and reuses it. Finally, we can write much more generic algorithms. We can write vector multiplication that uses with any user-provided types. And we can improve the Boost.Spirit library significantly. Now the Boost.Spirit library could parse data directly to the user-provided structure. No macro. You do not need the Boost Fusion create structure, something ugly. You do not need to use the Boost.Spirit register structure or something like that. Just put a structure into the rule of the Boost.Spirit and that's it, it will work. Looks awesome for me. Okay, a few more examples to convince you. Oh no, compile times. People sometimes ask me, well, those tricks seems really heavy. Will the code compile for an insane amount of time? Will I start compiling my project and my children will grow old before it will finish? The answer is no. With your children, everything will be okay. And here's why. Slides are simplified. slides you're seeing are simplified, sometimes significantly. For example, when we were detecting fields count in linear time, dropping one argument after another for a long time, doing this one by one, the actual implementation uses binary search in here. So it, in binary logarithm time, can detect fields count in your structure. That's awesome. What does it mean in practice? In practice, that means if you include an IOStream header, all the parsing and translation of that IOStream header will consume much more time than all the metaprogramming tricks you saw. You just won't notice that there's some reflection of the structure. And now a few more examples to convince you how it is good. Now, let's create a structure, comparable structure, and an insane amount of fields in it. Some integers, short, chars, booleans, more integers. Writing a less operator for that structure is insane. Well, Stefan yesterday told that you can use Boost.Type for that. You can just use Boost.Type for writing a less operator for such structure. Yes, you could. But if you modify that structure, swap a two fields structure or add another field, you need to fix all the comparison operators and add or change the definition of your comparison operator. If you use previous metaprogramming tricks, you do not need to do that. Everything works out of the box. You just can put your structure into the stud set and that's it, it works. Also, out of the box, you can serialize your structures. Just put them into any output stream. You can write them to the file, that's it. That's a working example how to serialize a set of your structures. That's it, nothing more. You do not need to write the OStream operator for that insane structure. Everything just in here. You can also deserialize your structure. You do not need to write the eStream operator for your structure. Everything works out of the box. Just grab the information from the file and that's it. My favorite example, because nobody understands it, it's a flat type function. That function allows you to initialize your structure from tuple. You just write struct my structure, field integer, and field short. Then you create a variable s, structure. And after that you write flat type structure equals tuple. After that line, the int field will have the value 10, the short field will have value 11. That's it, that works. So, at that point, we got a working solution for C++14 with some minor issues. For example, it loses information about enums, it has some limitations with pointers, it flattens your structure, it has a reinterpret cast, but it works. And works well in C++14. But it has a reinterpret cast. And I hate those. Reinterpret cast doesn't allow you to mark your function with constexpr. If you write flat get function that has a reinterpret cast in it, you cannot mark that function constexpr. Std_get is constexpr. Our flat get is not constexpr. I don't like it. Let's fix it. The fix is pretty simple, about a megabyte of code. We'll just write it down in a minute. The solution is really simple. We got structured binding in C++17. And it allows us to decompose a structure into fields. That's it, we've got references to the fields in the structure. That's awesome. But we need to know the exact count of fields in the structure we're decomposing. Otherwise, it won't compile, and I do not know, it looks like impossible to use structured binding to SFINAE something out. Or not. Nah. But we already have a function that detects fields count. It's first slide. And it works at compile time. It has no limitations. The only limitations is that the only limitation is that structure T must be aggregate initializable. That's the same limitation that the structured binding has. Now, we can create an integral constant from fields count. We'll create a tag, and then we'll make a lot of estuple impl functions, and we'll use a tag dispatch for that. We'll just generate a lot of estuple impl functions for different amount of fields in the structure. If our structure T has one field, the first function will be called, and it will decompose our structure into one field. After that, we create a tuple of references to that field, and just return a tuple. If our structure T has two fields, the second function will be called. It will decompose a structure into two fields, create a tuple of two elements with references to those fields, and it will return that tuple. The good point is, the best part here is that those tricks work at compile time. And they do not do flattening, they do not have, they do not lose information about enums, they have no limitations on pointers depth. No limitations at all. Only your structure must be only aggregate initializable. That's it. After that, you can write a std_get that works with user-provided structures at compile time, and that's it. Everything works out of the box. Now, that was the end. Thank you very much for being patient. Thank you for tolerating my Russian accent. Thank you for tolerating tuple instead of tuple. You can find the source code of the library at the GitHub. Here's the link. The link is also on schedule for C++. For CppCon 16th, there's only one thing that could make you a little bit nervous. I've renamed the library. Some people told me that magic doesn't sound well, so I renamed it into the PFR library. Nobody knows what is that, but it's now named PFR. And it also has some Boost markup now. It's in the Boost namespace. I hope that one day it will be a part of the Boost libraries. At the GitHub, you can find a lot of documentation, a lot of functions that were not described here, a lot of other nasty stuff, examples, whatever you like. Now, thank you again. Thank you. Questions?
Wonderful talk. Thank you very much. So except for the last part about C++ 17, I was wondering if this can even be implemented in C++ 11, and if so, what changes are required?
Yes, it could be implemented in C++ 11, but there's a lot of things that I removed from the slides. For example, there's a lot of static asserts that ensure that we have the correct layout, or that we are working with plain old data type, or that this is not a user-provided constructor, that we haven't called the user-provided constructor or initializer list. In C++ 11, some compilers refuse to have a static assert and return in constexpr function. And that's bad. We will need to remove all the static asserts, and that's not really good.
Thank you.
I have one question. If you use an aggregate initialization with an equal sign, then you can omit those braces. And that flattening of a structure will be automatical. Can't you just use it and forget about all the other stuff that we're doing?
I've tried to do so, but compilers were making a lot of warnings in there. That's it. And no, it won't help you. Somehow it doesn't flatten. It requires another curly brackets most of the time. If you just provide a lot of arguments in there without curly brackets, the compiler says, nah. In that way, it works. That's it.
Okay, maybe that's a compiler bug. Okay, and the second question about reinterpret cast. Couldn't you just find an offset of a structure of a beginning of an element instead of reinterpret casting all this structure to unknown tuple size?
Yes.
And you already get it in those array that you use for indexing.
Yes, you can do it, but you will also need to reinterpret cast the
But
thing.
you don't need to be dependent on a layout of a tuple.
Well, yes, but with tuples, it's simpler. You do not need to count those offsets by hand. And there is a big problem. Different compilers do the alignment in different ways. There are border cases where they behave absolutely differently.
But isn't that array with array type, with type numbers and zeros already have that layout there? When there is not a zero, that is the beginning of a...
Not exactly. For example, if you've got a structure, I'll give you an example. Structure. No, I won't give you an example. But it doesn't work that way.
Oh, okay.
There are some cases where it doesn't work. If you get a pointer, it will force the alignment of 4 or 8, and then if you get to unsigned char. No, I won't tell you that.
Okay, thank you.
Right now.
Anyway, awesome talk.
So just curious, is it possible anyhow to bypass the flattening of encapsulated structure? So in a place where you essentially do figure out that this is a structure and it contains this many elements and you're dumping it into a parent array, if we oversize the initial array, say do triple size off, then we would be able to write at least something like some code corresponding to opening curly brackets and closing curly brackets, and at least for the purposes of serialization, we would expose the underlying structure.
Yes, it is possible, but the result would be the same as with flattening. We'll lose information about the exact type of the structure. Yes, we will know that those 5 fields are located in the structure. But when we'll be writing the comparison operators, we'll just need to go in there and do the flattening again. When we'll write the less operator, we will just detect that there's some structure or some tuple. We need to go in there. That won't help a lot. Have I answered your question?
Pretty much, yeah. Any hope that at some point we could magically get the names of the members? C++, 31 perhaps?
There is a reflection proposal. I hope it will be in there so I just can forget about all that stuff.
Okay, so awesome talk first. I have another question regarding implementing this in C++11. So besides the issues related to assert, do you have guidelines to replace auto and other functionalities that have been introduced in C++14?
Yes, you could replace the functionality. You can make index sequence and other stuff by hand. You can remove the static asserts and rewrite all the constexpr functions to be recursive instead of having loops in there. So probably yes, that is possible. But I've tried a few times to do so, and the static assert was the thing that stopped me. I do not want to risk here.
Okay, thank you.
I've got to reinterpret cast. That's enough. No more.
First of all, I just wanted to say it was a fantastic talk. Thank you. And your Russian accent's perfectly fine. I think we understood it. This is a half-joking question, but at any point did you put time into thinking about bit fields?
Bit fields. I've put time into thinking about bit fields, but you cannot get the width of the bit field using the implicit conversion operator. It will just give you, if we have a structure and there you have a stud size t, 2 dots, one during the implicit conversion operator, when the implicit conversion operator called, it will be called for stud size t, not for the stud size t with 2 dots and 1. And the another limitation is in C++17. We cannot create a reference to the bit field. So probably if you have a bit field in that structure, that will be a compile time error. But there is no C++17 compilers right now. I cannot test that code. It's highly theoretical.
All right, thanks.
I hope it compiles, at least with minor modifications. Yes?
Hi. My understanding, if I've got this right, is that when you have a structure that contains another structure, you're aliasing that to a structure with the field, a structure 1 level deep that with the fields flattened out.
Yes, that's right.
Is that really layout compatible? I think the padding can change in that situation.
Yes, it could change if you've got a, or not. I need a picture. Double. Just a minute. One structure, it has a structure double in the char array. The first structure A will force the alignment of double for the second character. And that's it. It could be optimized if B is derived from A. In that way, some compilers do optimize it. But if it's located in that way, no, they do not put char inside the A. Am I right?
No. So this is the substructure. So here is the substructure A.
Oh yes,
The
now I
last
understood
character will
you.
be out there because it has to be out there for
Yes.
byte-wise
In that case, the size of the structure will change, and that will trigger a static assert. There's a lot of static asserts for that cases. Why?
Because the size of will be padded out to make it the right alignment for arrays.
2 chars will be together in
No,
that example, no?
Because this has to be byte-wise copyable.
Just a moment. Now, that structure will have a size of...
No, you're right. That'll be
Yes.
longer.
Yes. So the static assert will be failed. Another question?
Yeah, another question. I guess that using those types you used to determine the size of and the types of a structure, you can use it to determine the number of arguments and types of a function. It's basically the same code. Is it available in your library?
No, I haven't thought about that, and you can even detect the types of those
it's
arguments.
mostly the same code.
Now you just gave me a few more nights without sleep.
I'm glad you did.
Thank you.
Okay.
Any other questions? Great. I'm free.